Can you see the slides? Thumbs up would be good. Great, thanks a lot. The first problem we want to look into is, am I audible also? There was a problem from somebody that there was a bit of audio issue. Now is it okay?
You are audible, sir.
Great, thanks a lot. The first example we are concentrating on, it is a spotlight beam of intensity I nu is equal to 5 × 10⁻⁸ ergs per second per centimeter square per hertz per steradian at a frequency of 5 × 10⁻14 hertz, pointed at a cube of gas. On the opposite side of the cube, a detector which responds only to light at 5 × 10⁻14 hertz measures the intensity of the light to 3 × 10⁻⁸ ergs per second per centimeter square per hertz per steradian inverse. The spotlight is turned off and the intensity of the light emanating from the cube at the same frequency is then measured to be 2 × 10⁻⁸, the following units. Okay, so there is a spotlight beam of intensity I nu given over here, and at a frequency of 5 × 10⁻14 hertz. That means so it's pointed to a cube of gas. On the opposite side of the cube, a detector which responds only to the same frequency measures the intensity of the light as 3. Okay, so it was initially at 5, it went to 3. The spotlight is now turned off, and the intensity of the light emanating from the cube at the same frequency is measured to be 2. Okay. So what are the optical depth and source function of the cube of gas at this particular frequency? Okay, that's the question. So the classic question, if we go back to the radiative transfer part, you have some kind of a cube. So this is not the right. Just a second, let me draw a cube. Yeah. So you have some sort of a cube. The best of my ability, and you're shining some spotlight beam from this side. The I nu over here is given at S. It traverses S plus ds and comes out of there as I nu prime at S plus ds. So I nu is known, I nu prime is known, and then when everything is off, the particular gas in the cube is emanating at particular intensity is also known. So the question asked is that what are the optical depth and source function of the cube of gas at this particular frequency? That's number one. Number two is if the cross section of the interaction between the photons and the gas particles is 5.7 × 10⁻⁸ centimeters square, the cube is 50 centimeter in length and uniform in density. What is the number density of the gas particles? Compare the source function of the gas to the intensity of the spotlight beam and contrast these two objects as sources of light. What does the source function tell you about the foreground object? So it looks a bit complicated, but let us go ahead and try to take it one by one. Okay. So we have two unknowns, the source function and the optical depth. There's an equation we have using this I nu, this part is already known. We have been using this particular expression before when we did the transfer. So when the spotlight is off, there is no incident intensity. So I nu naught is equal to 0. And so in that case, I knew not, I knew off is just going to be represented by the S nu 1 minus e to the power minus tau. Okay. When it is on, then it is governed by this particular expression. So this is the absorption part, and this part is talking about the emission. Okay. So if I subtract the two equations, you suddenly get an expression with I nu on, I nu off, and I nu 0 e to the power minus tau. So if I do plug in all of those values, this is on one is when it goes on, then it is saying it is 3. Then when it goes off, it is 2. And I knew not is basically the original one, which is equal to 5. Okay. So if I do all those things, then finally I get the value of tau is equal to 1. Tau nu as 1.61. And so if you solve the source function, you put in back into this particular expression, the value of tau into this expression, and you can figure out what the value of S nu is, which is given by this. Okay, so that's the quick and easy part. Now, you have the absorption coefficient kappa nu, which we discussed earlier, and that is equal to number density times sigma nu. Okay, and what is sigma nu? That is given as 5.7 10 to the power minus 18 centimeters square. Let's go back and figure out what this is. So if I go back 2 slides, this is given as and the gas particles, the cross section is given by 5.7 10 to the minus 88. Yeah. So then this absorption coefficient is the number density multiplied by the cross section. Cross section is given, so you can then kind of know what the. So if you know kappa nu, then you already know sigma nu, so you can derive what n is, because that's what you want to know. Now tau nu is already known, that is 1.61. We have done it already in the previous slide. So tau nu is equal to kappa nu times L, because it's a cube, so we know the sides of the cube. So if you put that in, each side is 50 centimeter. The length is 50 centimeter also. So if we put that in the expression, I get from tau nu is equal to sigma nu times L into L n. I know sigma, I know L, and I know tau. So I can calculate what the value of n is. That comes out to be 5.65 10 to the power 15 gas particles per centimeter cube. Okay, that's our 2 questions we have to answer. Now let's go and check the third one. The third one says, compare the source function of the gas, the intensity of the spotlight beam, and contrast these 2 objects as sources of light. What does the source function tell you about the foreground object? The source function of the gas is smaller than the intensity of the spotlight. Okay. This indicates that the gas is fundamentally a weaker light source at this frequency. The source function indicates the brightest the gas could get on its own, and this is less than the intensity produced by the spotlight. So essentially, you have the source function was given by S nu. The original spotlight have this thing of I naught nu. So definitely this was 5 in the units, and this was the same unit. It was around 2. So definitely the source function of the gas is weaker than that. So it's a bit, it looks a bit complicated, but then when you put in the knowledge you already have from the transfer, then it becomes easy. The only new part which we learned over here is that the kappa is a product of the absorption coefficient, the product of the number density of the gas and times the cross section. So this is something which we learned new. Okay. Okay. So now going forward, the second example, we have consider an electron that undergoes simple harmonic motion in y direction. The y position is given by y is equal to y naught sine omega t. What is the time average power of the radiation produced by this oscillating electron? So the acceleration of the electron is as a function of time, taking the second derivative. So d2 by d2, the second order differential equation, is equal to minus omega square y naught from sine omega t. Now that is already given. So you have the formula of the Larmor formula, where P is given by 2 times Q square, which is the charge, times A square by over 3C square. So if I substitute the equation, we get PT is equal to 3E squared over 3C cubed minus omega squared y naught sine omega t. Okay, so the acceleration part we are replacing by the d2y dt2. So you have P, the Larmor formula is 2q squared over 3c squared, sorry, and it was having a square. A square is nothing but d2y dt2 whole square. So you get the double derivative of y from here, which also we call is y double prime for easier notation. So we put this over here, and finally you get the answer, the Larmor one. Okay, and the time averaged part, so this still has an omega t. So if you do this time averaging part, you finally get the value of e square omega to the power 4 1 square divided by 3c. This is the formula. The only trick over here is to relate the acceleration with the double derivative of y. Okay. Example number 3, an electric stove is turned off and the heating element or burner turns from red back to black, but the stove warning light indicates that the stove is still hot. An infrared sensor is aimed at the burner, and the radiation at a frequency of 3.33 10 to the power 14 Hertz emanating from the burner is determined to have an intensity of 1.4 10 to the minus 15 ergs per second per Hertz per centimeter square per second. If that is so, then estimate temperature of the stove burner, that's 1, and estimate total flux of electromagnetic radiation emitted by the stove burner. So we have a frequency that is 3.3. So frequency is 3.33 10 to the power 14 Hertz. And the intensity is given by 1.46 times 10 to the power minus 25, the entire unit. I just put in a whole lot of terms on there. So we do compute temperature of the stove, that is one, and total flux of electromagnetic radiation of the stove bar. Let's go ahead. The stove burner is solid and opaque, and so the Planck function is a good approximation to the intensity emitted. It is no longer in the Rayleigh-Jeans limit, so we cannot use this. This frequency is pretty high. It's close to 10 to the power 14 hertz. So h nu by kT, the Boltzmann times T, is less than the 1, does not hold anymore. So if you use the this thing, Rayleigh-Jeans limit does not hold. So Rj limit does not hold in this case. Okay. So to solve the temperature, we rearrange. So we have this Planck function, which is fine. We rearrange the above equation and we rewrite it as minus this thing. So you put the value of I nu, put the value of nu, and the h and k are constant. C is also constant. So if you put all of those values in, finally you get the T. It's basically simple. It's a little bit more of a calculation. So this kind of thing comes and asked in an exam-like scenario. First thing you have to understand is this frequency, whether the frequency is low enough to apply the Rayleigh-Jeans limit. That is the first question you should ask yourself. This is clearly pretty high, in 10 to the power 14, so it is not near the lower frequency of radio regime. And so Rayleigh-Jeans limit not hold. So if you use the actual expression over there, it's a bit tricky because the only thing you concentrate on is the nu. I have to check what the value of nu actually is. So if it is close to like a few tens of gigahertz, it is still not the approximation, but it's not this much higher than that. 100 gigahertz or more than by the Planck's law. So there's no exact clear demarcation where it holds and doesn't, but we can take a few tens of gigahertz is still okay. They apply Rayleigh-Jeans, but those hundreds of gigahertz, then you should stop using the actual Planck function. You can actually make the calculations and try to see at which frequency exactly it breaks down, but that's our field for this particular course. Okay. Okay. Since the burner, so we have to still get the total flux emitted. So that is sigma to the power 4 by Stefan-Boltzmann law. And if you just simply put T over there, you get the flux. That's it. The entire example is very simple, provided you don't make a mistake in using Rayleigh-Jeans in this particular case. Once you do that, this is perfectly fine. Next example, volume of ionized gas in interstellar space is known to emit thermal radiation at a frequency of 400 megahertz. Flux density of 200 Jansky is determined to come from an area of the sky with a solid angle of 2 × 10⁻⁵ standard view. If you have any question, you can stop me and keep asking. It's absolutely fine with me. Use this data to infer a lower limit to the temperature of this gas. Okay, so you have the I nu, calculate the intensity from the flux density and solid angle. So you basically have F and you have the solid angle. So derive the I nu from there. Okay, and then since setting the Planck function as the upper limit to this intensity and substituting in the values, we finally get the temperature should be lesser than equal to, sorry, greater than equal to 2040 Kelvin. So use the Planck's original function and put the values of I over there, just like the previous example, and you finally get an upper bound. Sorry, a lower bound of the temperature. Okay. Next example talks about cyclotron frequency. The strength of the magnetic field in a sunspot can be as large as 1,000 Gauss. What is cyclotron frequency of electrons in a sunspot? What frequency radiation do these electrons emit? So the equation is omega c is equal to the V perpendicular over R. If you use cyclotron, you get ED over MC. So omega c, if you just simply substitute the values, you finally will get that equals to 1.76 10 to the power 10 radian per second. The conversion of calculation may be confusing. Here, the CGS units of magnetic field are force per charge. So one Gauss is so and so. So you just rearrange the particular. You have to express the Gauss in terms of the CGS units and do the calculation. So one Gauss in its more fundamental units are gram centimeter per second ESU inverse. So if you do that, put that from Coulomb's law, and then finally you have these changes. You put it there, and you finally get in radians per second at a very Gauss frequency. The emitted radiation occurs at a frequency of mu c, and omega c over 2 pi, because omega c is just a cycle frequency. So it's 2.8 kilohertz. Again, it's actually very simple. You just have to use the right expression. The next example, we have a radio observation at a wavelength of 6 centimeter is the determination that a particular radio source has a solid angle of 7.18 into the minus 6 steradian, is opaque and thermal, and has a flux density of 250 joules. So its wavelength is given as mu is equal to, sorry, we have been given a lambda as 6 centimeter. So you can calculate the mu from there, C over lambda. And it has a solid angle of 7.18 times 10 to the power minus 6 radian, and a flux density of 350 joules. So what is the temperature of the radio source? Let us see how do we go about it. So as it is 6 centimeters, so 6 centimeter corresponds to how much? So frequency is given as C over lambda. We have 3 10 to the power 8. Actually 10 because it is centimeters, so this is 6. So you have it's about 5 gigahertz. Yeah. So frequency is about 5 gigahertz. And you still can approximate this in terms of the religions. So if you do that, then you can use the brightness temperature expressions. This is TB. You put all the values, then TB comes out to be 63 0.6 Kelvin. Okay, again, you have to judge. So, next question was, what is the intensity of the source at a wavelength of 2.7 centimeter? And what is the flux density of the source at 2.7 centimeter? So, intensity of the source at 2.7 centimeter is corresponding to a frequency of 11.1 gigahertz. And there you can simply use this and get the final intensity value. Since you know the temperature, you can just put it back and then calculate the I, this time for a different frequency. So you essentially use the same expression, but here you have a temperature and you have two different quantities, the frequency and the flux. The intensity both have changed. So you can just plug them, you can just calculate the others because you know the intensity, sorry, you know the frequency and the temperature. So you can calculate the intensity from that particular expression. And it has been given a particular solid angle, so you can calculate the flux density as well. Okay. So in the first expression, knowing the flux density, we calculated the temperature, the brightness temperature. In the second one, we used the brightness temperature, and we knew what was the frequency at a different frequency at which we could evaluate the intensity, and we did that. Once we got the intensity, then the flux density can be just a multiplication with the solid. That's how we got it. Okay. Now, third, there is the third expression, third question. Let us go back. An observation is made at another opaque radio source that is twice as hot as the first source. What is the intensity as 2.7 centimeter? So the other source is twice as hot as the previous source. The previous source, the brightness temperature is 63.6. So here you just simply multiply by a factor of 2. So if you go by that, you already have, you don't need to even calculate. You already have the flux density at 2.7 centimeter. Now for a source, which is PB equal to 63.6. So for another source, which is have a twice TB as its own temperature, then this expression has to be so it is calculated the intensity was previously 2.41 into minus 14. In this particular case, it is 4.82, just twice of that. So intensity is not just a scale. So PV becomes twice, the intensity also becomes twice for the same frequency. Okay, what is the brightness temperature of the source discussed in the previous example? The source of wavelength lambda equal to 6 centimeters. The source is opaque with thermal radiation and has a temperature equal to 63.6. So its physical temperature and brightness temperature. Next question, next example, a spherical region containing only ionized hydrogen gas, 10 pc in diameter. So what is 1 parsec? You remember what is 1 parsec? Approximately 3 times 10 to the power 18 centimeter. Okay. So this 1 parsec is observed to have a spectrum that fits nu square at lower frequency and nu to the power minus 0.1 at higher frequencies. The turnover frequency occurs at 5 gigahertz. At 1.7 gigahertz, the measured intensity of radiation is I nu is equal to given this. Assuming the gas is of uniform in density and temperature, infer temperature and density of the hydrogen gas. So we have the size of the region, a spherical region. It is for the diameter is given as 10 parsec. And we have two different parts of the spectrum. There is at the lower frequencies, this has it goes down as a, so if I just plot spectrum, so if we have yeah, so F, yeah, so you have a inverted spectrum, something like this. So if we have log of F nu times log of nu, we have roughly nu to the power nu squared. So as nu rises, this thing also rises, and this is inverted because as nu rises, this spectrum falls. This is about nu to the power minus 5. Okay, so typically flux is kind of proportional to the frequency. Typically, the synchrotron radiation you have n minus alpha. So if I know fluxes from different frequencies, we can equate having a constant so F0 times nu to the power minus alpha. Okay, so in the lower frequency, this thing behaves in terms of this thing. So how do we go from here to there? Now, if you take log of both sides, that equals 10. So log of F nu is nothing but F nu over F nu F0. Whole log of that is nothing but minus alpha log of nu. And there's something called log nu, right? Okay, so that minus alpha, now if I consider to plot this, so log of F nu over log of nu is basically a straight line with the slope of minus alpha. That's how you draw this kind of plot at the end. Okay, so just starting again, we can again discuss, but let us move on and let us see how we are going to answer this question. Or we can again come back and discuss this while we are attending this question. So we can use the intensity at a frequency well below the turnover, where the emission is optically thick, to infer the temperature. At 1.7 gigahertz, which is below the turnover, the intensity is related to the gas temperature, and it is given by the Rayleigh's standard Rayleigh's law. So I can calculate, we can calculate the brightness temperature because we know everything else. Okay, nu is 1.7 gigahertz, so 1.7 C is known, and I nu also is given. So that brings us temperature, the brightness temperature, or the gas temperature is equal to 10,300 Kelvin. Now, as it's opaque, So the optical depth is equal to 1. And if that is so, then you can just write down in terms of the temperature. Okay, and we finally get this is equal to what was the original question? Yeah, so the original question says turnover frequency. So at the intensity of radiation is given by this, assuming then in for temperature and density of the hydrogen gas. Like, so to compute the temperature and density of the hydrogen gas. So temperature we have already done. Relative to the density. So this comes from a radiative transfer equation. If we have the optical depth is equal to 1, you can relate this. This is the function of emission measured, and so the EM is equal to the other constant, and then we put the frequency, the 5 gigahertz corresponding to 6 centimeters, and the temperature. If we do that, the emission measure comes out 9.3 10 to the power 7 centimeter inverse to the power 6 PC. And we know the electrons are Ni is equal to Ne, so the density is 3000 centimeter cube inverse. Okay. Next question. There's a magnetic field threading through the disk of the Milky Way galaxy. The magnitude is typically of the order of 2 microgauss, sorry. There is also an interstellar medium occupying the space between the stars that contains ions and free electrons. At what frequency do these electrons emit radiation due to their interaction with the galactic magnetic field? So we have seen this expression. The nu C is nothing but 1 over 2 pi E times the magnetic field over mc. Okay. Now, if I put all the values of P and electron charge and MNC, you finally get this to be equal to 5.6 hertz. It's an extremely low frequency and then below the lowest frequency that can propagate through the galaxy. Okay, so it's simple questions, just putting in. That's the thing. So synchrotron radiation we have discussed. So it's basically one of the non-thermal radiation. It has strong intensity, continuous spectra, directive radiation in the beam, polarized and pulsed. So we have a detailed description in the lectures, and the part which was interesting was that the flux as a function of frequency behaves as a part of power law. Okay, that part we have done in the previous thing. So we know that the flux density F mu is proportional to mu to the power minus alpha. The nu is the frequency where the flux is measured, and alpha is called nothing but the spectral index. Okay. So what happens is, supposedly you have a radio source of you're say looking at a radio galaxy at 2 different frequencies. But typically this is inverted. Okay, as I said, if you're plotting the log scale plot, that you're plotting log F mu over log mu, this will be basically be a straight line, but an inverted slope. So as the frequency decreases, the flux increases. That's the flux of the matter. So at a higher frequency, you get much lower flux than the lower frequency. So it's kind of lighter as you go to the lower frequency. Eventually, what happens is due to some phenomena of absorption, there is a turnover, which we were just discussing. And the frequency where it actually turns over is called turnover frequency. And we have various other reasons to worry for that. However, for a simple observation of any particular galaxy, radio galaxy, etc., we look for this particular trait. Okay, this particular feature, the spectral index, is a very important parameter, and we will show you how in the next 2 weeks. And this alpha has a lot to do with the basic nature of the medium which is emitting synchrotron radiation. And so what we do typically do, because this is a expression where there are 2 unknowns, right? Because you can write down the F mu as some constant and mu to the power minus alpha, right? So if we just have one equation, you have 2 unknowns, F mu naught and alpha. So what you do is we have typically 2 frequency of measurement. We do F mu 1, which is equal to F mu naught mu 1 to the power minus alpha. And you have another frequency, say F mu 2, which is F mu naught mu 2 to the minus alpha. And then you take the ratio of the 4. Then you see that F naught vanishes. You have observation of F mu 1 is observed and F mu 2 is observed. You know already the frequency mu 1 and mu 2 because that's a given. So by doing this, you can calculate alpha, which is nothing but log of F1 over F2 divided by log of mu 1 divided by mu 2. That's a very simple way of deriving the spectral index and knowing the exact nature. Now, this alpha is not fixed. It has a variation, it changes, it has different values it can take, and this listen to the lecture notes if you want to understand more. But for the purpose of solving expressions and problems, this is more or less sufficient. Okay. Next example, imagine a spherical synchrotron source with a uniform magnetic field 10 to the power minus 2 torch, angular diameter of 3 milliarcseconds, a spectral peak flux density of 10 Jansky occurring at 1 gigahertz. If instead the source's diameter were 5 times larger, what would its flux density have to be for its spectral turnover still occurs at 1 gigahertz? So we spoke about turnover, and it happens because of some particular phenomenon called synchrotron self-absorption. But essentially, the spectrum looks like this. It turns over at a frequency, you can say SSA. So the cause of this turnover is the synchrotron self-absorption. So SSA stands for synchrotron self-absorption. Yeah, and so that turnover frequency, it depends on the B to the power 0.5 and I mu to the power 0.4. So if I know the turnover frequency, I can calculate, and I know the intensity at a particular frequency, which is a measurable, I can actually constrain the field. which is associated. So that's a very powerful way. And we'll discuss this more in the next coming last 2 weeks of this particular course in more in details about these particular cases. Okay. Let us go back again and look at the question, what was asked. So a spherical synchrotron source, uniform magnetic field, B is given. Angular diameter is given to be 3 milliarc-seconds. Spectral peak flux density is given 10 Jansky, occurring at 1 gigahertz. So you have the kind of the turnover, the peak occurring at 1 gigahertz. So this frequency is 1 gigahertz. And you know the peak flux value, so you know the I nu. In this particular case, you know the B also, so you can put all of them together. And then you ask the question that if the source diameter would have been 5 times larger, what would be its flux density have to be for its spectral turnover to still occur at 1 gigahertz. Okay. So nu is the same. You have the flux density is given by IF nu as I nu times the omega, the solid angle, which is nothing but I nu pi theta squared over 4. So for the new source, it is 5 times larger in diameter. So this 5 theta goes to 25 theta squared. Okay, and so you can easily just calculate. And so keeping turnover frequency constant with a 5-fold increase in theta requires an F nu also increased by factor of 5. So everything remains the same. I nu is I nu also is the same. Just the omega just changes to 25 times. The flux has to balance it by 25 times in order to keep the turnover frequency the same. Okay, so that basically says that you have to have a flux. The new source with the 5 times larger diameter should have a flux is equal to 25 times the flux of the previous. So F prime is this, because theta prime is 5 times the past theta, which is the diameter of the source. Okay, that's again very simple calculation. The birth of next example, the birth of radio astronomy marked by the first detection of extraterrestrial radio frequency signals was an observation of radio emission from our galaxy by Carl Jansky, 1932. This emission, we know, is due to synchrotron radiation, indicating the plane of the galaxy is infused with relativistic charged particles in a galactic magnetic field. The spectrum of the galactic emission has been determined to have a spectral index of alpha is equal to -0.8. According to this data, what is the power law index of the energy distribution of the interstellar cosmic rays? So, alpha, which is spectral index, is 1 minus p over 2, where p is the power law index of the electron energy distribution. So that comes from the synchrotron radiation. I think for this particular purpose, it's better to know this upfront, because the theory will be covered in the lectures. For the purpose of this problems, you can just remember that the spectral index is related to the power law of the electron energy distribution by this particular formula. So P is 1 minus 2 alpha. So if alpha is known as 0.8, so P is known as 2.6. Hence, that's how the distribution of the cosmic ray changes. So here we're relating. So if we know, so coming just this discussion coming from the previous example, we can say alpha is coming from the observations of the same source at two given frequency, whether it's a radio galaxy or it is a galactic synchrotron emission. It is if you're taking data at two frequencies, and that can give you the spectral index. And knowing the spectral index by using some basic physics relationship, you can compute the power law index of the electron energy distribution, which is directly linked to the physics of it. So it's so the observations are now linked to the getting some science. So if you know how difficult the observations are, you slowly keep going towards it and getting physics and science term of the observations. So last example for this particular discussion, if the spectrum of the galactic emission has been determined to have a spectral index of alpha is equal to minus 0.676, sorry, and when observed at a frequency of 90 megahertz, flux density of 10 millijansky was observed, then what will happen? What will be the approximate flux density at 120 megahertz in millijansky? So exactly what we did, we have the flux now represented by S instead of F, but nevertheless the same thing. So if you know that this is the relationship, and if you compute, if you know the flux density at both frequencies, flux density at one of the frequencies, you know the both the frequencies and know the value of alpha, then you can calculate the flux density of the second frequency, which is given like this. It's a very common way to ask questions, numericals for the simple combination. Okay. Great. We can stop here for a little bit and try to